All right, so welcome everyone. It is my pleasure today to introduce Jacob Miranda. My name is Dr. Jose Javier Hernandez Ayala. I'm here with my two kids. If you hear any crazy sounds, I'm a associate professor at Sonoma State. My area is physical geography and climate science. Jacob is going to be starting his senior year next now in August. It's been a pleasure working with him. I'm very impressed with the work that we've been able to do over the summer, looking at the relationship between wildfires and hydrological processes in California. So Jacob is going to be presenting all of the work that we did between June and July, and I definitely have to say that very proud of the work that we've been able to do. So without further ado, Jacob, please show everyone what we did over the summer.
All right. So this is my presentation, well, our presentation, my bad, on the hydrological impacts of recent wildfires in California. So everyone knows with like the most recent fires happening, they're all over the news. That they're big, they're constant, and we wanted to analyze the extent as to, like, how much of an impact that these fires have had on the surrounding environment. So, our research question was: do areas burned by wildfires in the state of California experience significant changes in hydrological factors like evapotranspiration, vegetation cover, runoff, and soil moisture? Our hypothesis is based on the literature that we've read on this topic. We expect that the areas burned will experience significant changes in some hydrological processes, yet those changes and impacts could vary a lot. So I know, just jumping ahead a little bit, for some of the fires, there actually wasn't that big of a change at all, but I could say that for the most part, there was definitely negative changes. So, some of the literatures we've seen on vegetation and wildfires is that wildfires dramatically alter the vegetation patterns and ecological processes across broad landscapes. In forested ecosystems, fire effects range widely from negligible changes in canopy structure to a complete mortality of existing vegetation. And with individual fires, the shape, size, and configuration of remnant and stand replacing patches can determine post fire ecosystem recovery, including the maintenance or reconfiguration of vegetation communities. As for evapotranspiration, in the areas burned at a low severity, the evapotranspiration reduction in the first year after a fire averaged at about 224 millimeters in an annual year, which is about 31% of the pre-fire evapotranspiration, whereas high severity fires reduced uh, whereas high severity fires reduced the area's evapotranspiration by about 362 millimeters instead. Forest stands that were denser pre-fire had a larger evapotranspiration reduction across all burn severities. So, obviously, you have a bigger fire, then you're going to have more of a damage impact because there's going to be more waste everywhere to affect ecological structures. And this one we didn't really hit on as much, but it's still important nonetheless. Evapotranspiration reduction following moderate to high severity burns was greatest at about 900 to 1,300 meters elevation. So our data, we use the wildfire parameters from Cal Fire, specifically the top most recent ones, and we took those fires and we extracted data from them using the NASA Giovanni tool. The four main processes that we used was to were to analyze the vegetation using the normalized difference vegetation index from MODIS. We measured the evapotranspiration from NLDAS, as we did with runoff and soil moisture. And for anyone curious, NLDAS means North American Land Data Assimilation System. So our methodology was that we used seasonal time series for each of the 4 variables to construct data on the top 15 recent largest wildfires, so we could detect any major changes attributed to said wildfires. We would take the parameters, put them in the Giovanni, and then create a map that spanned about 20 years, including the year the fire took place, so we could see just how big of a change that area took. Before and after maps were then constructed in Giovanni to visualize the area that experienced the most hydrological changes. And then finally, anomaly maps were constructed in QGIS in order to quantify the changes in hydrological processes after the impact wildfires. So these graphs are of the seasonal time series, and the 4 fires that we chose that also had the biggest effect in the area was the August Complex fire that happened in 2020, the Scu Complex that also happened in 2020, the Thomas fire that happened in about 2018, 2017, 2018, and the North Complex fire that again happened in 2020. And as you can see, both the Thomas fire and I believe the August Complex we measured the evapotranspiration there, since those had the biggest effect, whereas the North Complex and the SCU had the biggest impact done to them in vegetation. So we decided to measure there, and the little red arrows show when the fire happened, when this dip in whatever measurement that we used happened. And then here we can see I used QGIS to figure out a map of the amount of for August Complex specifically. I used QGIS to figure out the amount of evapotranspiration that was measured in the area. Specifically, we used kilograms per meter squared. Now, this fire, it burned for about 3 months, a little less than 3 months, but from what I've seen, it is the only recent fire to have burned over 1 million acres, according to GIS. This fire was reported to be caused by a lightning storm, and from the maps, you can see that mostly the northwestern part of the fire was affected. Generally, the darker the color on these maps, the bigger the effect was. And it's very similar for the next couple fires as well. We have the SCU complex with its vegetation. Oddly enough, the SCU fire only burned for about a month, and it still nearly burned 400,000 acres. Again, it was caused by lightning, and this time the evapotranspiration mostly happened in the north and the south areas. For the North Complex, the vegetation was analyzed, but oddly enough, no units of measurement were given in the Giovanni tool. This fire burned for about 3.5 months. It burned a little over 300,000 acres, again caused by lightning strikes, and the vegetation mostly was altered in the middle part of the fire. And if you look at the bar graphs we have just under the map pictures, you can see that the numbers are still pretty low, maybe about 0.5 as a difference, but we have to keep in mind that no matter how small the numbers may be, the impact is still huge. Like the smallest amount of vegetation that has been burned away and is no longer there is still a major impact for all the wildlife, for example, that lives there / used to live there. Just thought I might as well point that out. And then the Thomas fire. Sorry for the map. I don't know what happened with Giovanni, but you can still see that this fire actually burned for about a month, a little over a month. It burned about 280,000 acres. This fire it did not have a specific reason stated, and the evapotranspiration was mostly affected in the eastern part of the fire. So our conclusions are that all fires have a deadly effect on the surrounding environment that can last for years after the fire is dissipated, as we could see with the seasonal time maps. Of the 15 fires that we analyzed, 4 of them, which were, again, the August Complex, the Scu Complex, the North Complex, and Thomas Fire, exhibited the most significant decrease in both vegetation and evapotranspiration in the areas burned. And the August Complex fire was identified as the fire that caused the most extreme decrease in evapotranspiration in affected areas. Here's all the references, just in case any of you were curious. And that is it.